let TUV equal XY, where X is equal to a function of GUV, and Y is a function of HUV, be a one-to-one C1 transformation with a non-zero Jacobian on the interior of the region S in the UV plane. It maps S into the region R in the XY plane. If F is continuous on R, then the integral of fxy dA over the region R is equal to f of GUV HUV times the Jacobian du dv over region S. So if we can integrate here in S, if we times that integration by the Jacobian, then that will equal the integral in R. So the nice thing about that is that's what that Jacobian does for us. That Jacobian is what we call the fudge factor. When I look at that Jacobian, it's a multiplier that I multiply my integral by in UV so that it's equal to the function in R. So let's see how this works. We previously worked on this problem 389 before in a previous video. And the part we found the transformation from S to R. And that's what we need here. We need a transformation from S into R. And that's what we have now. If you remember that, this was the video here. And our TUV was actually equal to 2U plus V minus 3V. That's what the transformation was. Now let's go back. Let's take a look at this formula here. So this tells me if I take this integral and I plug in my u's and v's, that's really what that's saying, into my function of x and y, and I times it by the Jacobian, and I take the du dv there, then I can say that that will be equal to the original integral. Okay, now what we were told to do here was we were trying to find the area, because part B says use the transformation T to find the area AR of the region R. So we just want to find this area. We could do this using a geometric formula, and we will, just to confirm our findings. But we're going to use the Jacobian here. So let's think of the transformation, because that's what we need here. So our transformation is here. Now I'm just going to take this and pull this information to the previous page. I'll paste it here. And what we're going to do is we're going to actually work out TUV. So really my equations are x equals 2u plus v and y equals 3v. So we're just going to find dx, du, which is 2, dy, du, which is 0, dx, dv, which is 1, and dy, dv, which equals 3. And then we're going to take the determinant of that matrix, and this is what the Jacobian is. This is our Jacobian. This is this component here. And notice here, they're taking the absolute value of it as well. All right, so it's going to be those two times together. So that's going to be 6 minus those times together, which is going to be 0. So minus 0, which equals 6. So 6 is our answer here. So we found the Jacobian now. Now what we're going to do is we're going to use this Jacobian in this integral here. And once we find this integral here, it's going to equal the integral of the original. And again, we're doing an area here. So let's get to it. Okay, so now, if we're going to do the integral here, the double integral, our Jacobian, and I'll just write that down below, JUV is actually 6. Okay, now we're going to use this information using that formula. So our f, our function here is 1, because remember, we're talking about an area. So the area of this, so our fxy is just equal to 1. because we're talking about area. And if we're talking about a volume, that we would have a function for that instead of 1. Okay, so then we have d, well, don't forget our Jacobian. Our Jacobian is 6. And don't forget the du dv. So now if I'm going to do my du first, I have to consider here my u runs left and right. So that means I'm going to start here at 0 for u, and I'm going over. And if you notice, what's stopping me is this line. This line is stopping me. So what is that line? We have to find the equation of that line. And the equation of that line is y equals, now remember here, this is a function of u here that I'm looking at. So this would be negative u plus 1. And this is just an equation of a line. And this shouldn't be y, actually. Let me write what it really should be. It should be v, because my v is my y here, and my x is my u in a sense. That's what we're dealing with for this one here, with this rectangular system here. All right, so we get v equals negative u plus 1. So what's going on here is my u is starting at 0, because it's starting all the way here, and it's going over. So I would say the lowest bound for u is 0, and the highest bound is the equation v equals negative u plus 1. But this is a du we're finding here, so we're going to have to switch that around here. So I'm going to have to solve this for u since I have du. So I'm going to move the u over, move the v over. So my same equation is going to be u equals 1 minus v. And that's going to be the same equation, as these two are actually equal. So hopefully you're okay with that. Just moving things around algebraically. Okay, so that's going to be my upper bound, 1 minus v. And then I'm going to look at my v here. Now my v is going to run from 0 to 1, and that's going to be here. The lowest it goes is 0, the highest it goes is 1. So that's our setup for this integral here. So now we're going to actually integrate it. But before I do, I want you to see how it looks next to the formula. So I go back here. Once I find it all, here it is. I'm just going to show you where everything's at in here. So here's my Jacobian. Here's my Jacobian. My HUV, or my FUV, excuse me, is here, and it's just 1 because we're talking about an area here. And then I have my bounds, and I have my du, dv, du, dv. Now again, I can change my order on that too. I could do dv before du, and that doesn't make a difference, just as long as all my other components are straightened out. Okay, so let's integrate this now. So we really have the integral from 0 to 1, the integral from 0 to 1 minus v of 6 du dv. So then the integral from 0 to 1, and when I integrate this 6 here, that's going to be 6u. And it's going to run from 0 to 1 minus v dv after we're done with that. So then we're going to have the integral from 0 to 1 still. And when I plug in the upper bound, it's going to be 6 minus 6v once I distribute. And when I plug in the 0 there, it's going to minus 0, which I don't have to worry about because it's 0. And then I have dv. So now when I integrate this here with respect to v, this 6 minus 6v, that's going to be 6v minus 3v squared. And that's going to be from 0 to 1. So then that's going to equal 6 minus 3, and that's when I plug in the 1, minus the lower bound, which is going to be 0 again for both of those. So my answer is going to actually equal 3. Now there's a few things I want to show you. I'm going to take the original area here, and all I'm going to do is draw a triangle here, and I want you to think about the area of this triangle. the area is equal to 1/2 base times height. So if I look at the base here and I see that base is 2, I'm just going to plug in my information. So that's going to be A equals 2 times the height, which is 3 here, times 3. And that's going to give me 6 here, and half of 6 is 3. So we see that this 3 confirms the actual area of the original region. What's interesting about that is let's take a look at our new region that was created by the transformation. So now when I come over to the U and the V here, and I think I'm going to pick a different color. I went with the green. When I pick that U and that V here, notice the area of this triangle here. That's also going to be 1/2 base times height. So that area is going to be 1/2. My base is 1, and my height is 1. So that area is going to be 1/2. Now remember, the Jacobian for this one was 6. So remember how that works. When I look at that formula here, what I do is I take that function and I take the integral over the region S, and then I times it by the Jacobian. Now take a look at this. That Jacobian here is 6. So that area here is 1/2. Now if I take that 1/2 for that area and I times it by 6, that's going to give me 3, and that 3 should equal the other area. And that's what we see here. So really what's going on here, when I do that map back this way, I'm timesing this area here by that Jacobian, and that Jacobian being 6, and then I can see why when I take that transformation back this way, I'm going to get my area of the original, and I'll call it AR because it's of the AR, that's actually equal to that 1/2 times the Jacobian, which is 3, or 6, excuse me, which gives me 3. And that's what we see here. So that's why I tell you that this Jacobian is really like a fudge factor here. And it just makes it equal to the original region that I'm looking for. And now we see why this formula actually works here. And that's really the beauty of it all, that I can use those Jacobians to get any area I want, but I can work actually in a nicer space. And not for this one, but more complicated problems I can do the same thing with, as long as I calculate my Jacobian and times it by it and then integrate.